Okay, welcome back, and now we're going to look at Newton's law in 2 dimensions. So the goal today, I can apply Newton's second law in 2 dimensions for real-world applications. And this is where your understanding of vectors is going to play a major role for us today. I talked about normal force, and the normal force is something that's extremely important. I want to take some time now to go through and talk about what that is. So normal force is the force applied perpendicular to a surface to balance Fg. Okay, so the normal force is the force applied perpendicular to a surface to balance Fg. So it pushes back. It's basically the Earth pushing back on force due to gravity, and the normal force is it can be whatever it needs to be. All right, it varies depending on what's being applied to it. What I'm more interested in is the second part down here, and it's applied forces in the normal force. Okay, so up above, for example, if we had an object, let's go with a box, sitting on the ground, you'd have your force due to gravity. So that means that normal force would keep that box from going or accelerating into the Earth, and your force due to gravity is equal to the normal force. Now, this is, I would say, it's definitely not always the case. I don't want to say rare because that's not also true, but what happens when we have something pulling or pushing on an object? So there's two situations I want you to consider here. And here's my surface, and we'll keep it simple, keep it as a box. Okay, so situation 1, situation 2. What happens if this box, you're behind it and you're pushing it? Okay, so if we're pushing it, my applied force, Fa, is going to look like that. So what forces are acting on this object, on this box? Okay, so I'm going to have some people that are saying, okay, well, you have force due to friction, because anytime you push something, force due to friction is a resistive force. Okay, we're going to have a force due to gravity, and we're going to have a force that's pushing the box. Is all of Fa, all the applied force, going to be going into pushing that box forward? Okay? And the answer is absolutely not. It is the x component, Fax, that's pushing that box forward. Because that vector is on an angle, okay, it's on an angle theta, not all of the force is going into Fax, or into the direction that you want it to go. There are two components acting here. Okay? There is your horizontal component, and there is your vertical component. So Fax, the force in the x direction, is your horizontal component. That vertical component, Fay, though, is pushing down. So that means that force due to gravity and force from you pushing downward on a box, you are working together. And that would mean that the normal force then is increased because it has to keep this box from going or accelerating into the ground. So that means that your normal force, Fn, has to be great enough to balance force due to gravity plus Fay. Okay? Has to be balanced. In the second scenario, what happens if this is a wagon, your favorite little red wagon? So now you're pulling something. What happens to those two vectors? Well, you still have a force in the x direction, so we'll have our Fax, but now the force in the y direction is in the upward direction. So that means that, my green ones are my final ones here, so Fax, and yes, you do have your force due to friction, which at this point in time is not overly important for me. We have force due to gravity down. And now we have a force from you pulling upward on it, upward on the handle. All right, you're still going to have a normal force unless you are pulling more than what the force due to gravity is. So now your normal force, Fn, is equal to force due to gravity minus Fay. So the normal force is as big as it has to be. All right. So up here, it's as big as it has to be. It's as big as it has to be. All right. It's not a constant. It's not something that you're going to calculate and say this is what it is for the whole scenario. It's going to vary from situation to situation. And it's extremely important, the normal force, in the future lesson when we start talking about some other key forces. So how do you calculate normal force? Well, normal force, the final formula I want to see on that cheat sheet is partially from above. So it's force due to gravity. So I'm talking about, this is true, okay, some of the time. But there could be additional forces added or subtracted. So it could be plus or minus your Fax, or sorry, your Fay, force in the y. Okay? So you can even simplify, or I can make that formula a little bit more clean for you, where Fg plus or minus the magnitude of your applied force sine theta. Okay? If the angle, if theta is 0, sine of 0 is 0, so then Fa doesn't apply at all. That would drop out of the equation. Plus, okay, would be for the situation where you are pushing down. Oops, pushing down. Okay. The subtraction would be from pulling out. All right. So this is extremely important to make sure it gets on to your sheet, because we are going to have to calculate normal force, and it is going to be extremely important as to why we are calculating normal force. Okay, so those vector components play a huge role here. When you push on something, when you're pushing the lawnmower, okay, cutting the grass with a push lawnmower, it's not all your force that you're pushing on that lawnmower is not going into motion or moving it forward. Some of it is pushing downward, which is actually making it harder to push the lawnmower. So keep that in mind. So one-dimensional forces, okay, they act only in one direction, obviously. Oops, act only in one direction. In one direction. And they are what we call linear. Okay? The vectors would, I guess I'll put all be linear. Okay? Two-dimensional forces don't follow that. Okay, they act in both the x and y direction, which means that to determine unbalanced forces, or Fu, we need to use our knowledge of vectors. Okay, so for unit 1, our unbalanced force is going to equal the forces in the x direction plus the forces in the y direction in terms of components. All right, and we're going to have to use magnitude of Fu. So this is already on your first cheat sheet. The components, if you want to find the angle, tan inverse of the y component over the x. Okay. So a bit of a review as to what's coming up here in the next couple of slides. All right, so moving along. Determine the acceleration of the object. Remember, acceleration is a vector, so that means we need both vector, so we need magnitude and direction. So what I would recommend for this one, all the numbers are given to us here. So what I would say is I'm going to do unbalanced force is equal to the forces in the x direction plus the forces in the y direction. So unbalanced force would equal, and again, my system up and to the right is positive. So my x direction would be the 21 and 37. So it'd be 21 minus 37 I. So I don't actually have to find components. I don't have to use trig here. Plus forces in the y direction, up is positive. So 20 minus 30j. So that means that my unbalanced force would be negative 16I minus 10j. If I want to find the acceleration, I need to know the magnitude of the force, and that is the square root of the x component squared, y component squared. So negative 16 squared, negative 10 squared, and that would give me 18.9 newtons. Now I need a direction because this is a vector. So I have to find the angle. So tan inverse of y over x. So tan inverse would be 10 over 16. So this is exactly what you were doing before in the first unit, right off the start of the course. So we'd have 10 divided by 16 tan inverse. And I end up with 32 degrees. Okay, so we want to find acceleration. So Fu ma. So the unbalanced force was 18.9. The mass of the object is not given. So let's give it a mass. Just over here, let's put mass is 10 kilograms. Makes the math a lot easier. So my acceleration would be 1.89 meters per second squared, and the direction would be, it's in the same direction as my unbalanced force. So x component's negative, so that means I'm going to go west or left, doesn't matter, 32 degrees, and the j component's negative, so that means I'm going to go down or south, so you can use either of those notations. So therefore, the acceleration is 1.89 meters per second squared, west, 32 degrees, south. Okay. So we are just using our vector components. So this one, the vectors, the values were already calculated for us in the x, y direction. So it made the math a lot easier. That means we could just jump to that vector notation, which allows us, and remember I said, it's always the same when you're finding magnitude and the angle algebraically. Okay, I'll stop the video there and I'll continue in the next one to finish up some more examples.